So welcome back. So welcome to the last talk of the day, and I remind you that afterwards there's going to be the cocktail party, so I hope everyone will join. And before I announce the last speaker, I want to say that I hope maybe you have seen that on Thursday we're going to have an open problem session in the afternoon. So for that, I invite all of you, if you want, to present an open question or an open problem. So if you have something that you would like to present, please approach one of the organizers, and then we can make a plan for that session. Okay, so I will maybe say this again tomorrow, but if you have an open question or an open problem that you want to present, please approach one of the organizers. And now, let me announce Marta Panitsut from Norway, and she's going to talk about positive del pezzo geometry.
Okay, yes. First of all, thank you. I would like to thank the organizer for having me. As a PhD student, I attended one of the first meetings that were mentioned this morning, like a tropical geometry in the tropics. So I'm very happy to be back now from the Arctic to the tropics. Right, so this is a joint work with Nick Early, Alhadis Geiger, Bernd Struenfels, and Claudia Ayun from some years ago. A couple of years ago, we were all based at the Max Planck Institute in Leipzig at that point. And we want to study positive geometry of the pezzo surfaces and their moduli spaces. So positive geometry is a new area that is getting established recently at the interface between physics and combinatorics and geometry. Okay, so in particularly in the connection with physics in the studying of scattering amplitudes. So here is an example. So when studying one of the integrals, consider when studying scattering amplitudes, it's this integral here. So what does it mean? Well, we are considering the interaction, collision of 5 particles, okay, in this case. And these integrals, okay, tells us the probability that a certain phenomenon appears when these 5 particles collide, okay? So this Sij that we see here as exponents, these are called Mandelstam invariants, and these are the relevant physics quantities, okay, that are measured and that are interesting for the physics. But what's interesting, maybe more interesting for us, it's what's appear here at the integration. So that's M05 plus. So M05 is the moduli space of 5 labeled points on P1. Okay. So while modding out a GL action, and then also, so by fixing a projective basis, okay, and modeling out also a torus action, well, we can represent these 5 points as the matrix M there, okay? And then when I ask that the 5 points to be distinct, I want that the 10 maximal minors of this matrix, so the Pij, the 2 by 2 minors, don't vanish, okay? So in total, we get these 10 Plücker coordinates. Some of them are constant, some of them not, and I want the constant one to be different from 0. Okay, so I can define M05 by an inequality. Okay, so I want this product to be different from 0. Okay, so the Pij that appear here in this integral are indeed the Plücker coordinates. We can think of them as Plücker coordinates. Okay. So now, when working on M05 or M0n in general, it's very normal to consider cross ratios, coordinates. Also, this called dihedral coordinates. Okay, so there are these 5 coordinates I'm representing here in terms of the Plücker coordinates. And it turns out that they satisfy the following systems of quadratic equation. Okay, so we have 5 quadratic equations in these ui variables. Okay, and this gives us an embedding of M05 in a 5-dimensional algebraic torus. Okay. And this, we will see this also later on. This is an example of what now is called a binary geometry. Okay, so binary means that, for example, well, if I ask one of the variables, okay, I move to the boundaries, sorry, and I ask one of the variable to be 0, okay, then, for example, this will, if u1 is 0, then u2 will be forced to be equal to 1. And also u5 will be forced to be equal to 1. So this is the binary nature. When we impose some variables to be 0, some of them gets equal to 1. Okay? Now, if we look at the real points, okay, now instead of I look at the real points of M05 in this embedding, okay, and we see that there are 12 regions, okay? And one of them, we call it M05 plus, okay? So this is the positive region. So this is the region where all my variables are allowed to be positive and still satisfy those equations, okay? And this region looks like, you can try to imagine and drawing, it looks like sort of a curvy pentagon in R5 plus, okay, positive. All right. Now, moreover, this is the region where the following tropical positive equations are valid, okay? So I can turn my u variables into v variables and tropicalize the equation, okay? And so the tropicalization of this positive region will become a cone over a pentagon, okay? So in particular, if you know the structure of the tropical Grassmannian 2,5, which is a cone over the Petersen graph, you see one of the pentagon in the graph. Yes?
Quick question. In your first slide, you had the epsilon that you didn't say what it is?
Yeah, well, I'll come to that in a bit.
Here, the map is, you say embedding, but I think you're giving a rational map. What am I missing? UIs are rational functions.
Yes, okay, so maybe, yes, but it would be fine because I don't want the Plucker coordinates also to be zeros, and so, yeah, yes, yes. Mm-hmm. More questions? Okay, now what happens, so there is this epsilon, which is like a epsilon that they consider in the integral, okay? And what happened is that, well, this, the integral, that function that I define is transcendentals in general, but miracles, magic, when this epsilon tends to 0, this turns into a rational function in this Mandelstam invariance that we were considering, this Sij, okay? And this is really what they want to compute. So this function here is amplitude, and is this function that measures probability of certain events happening, okay? What happens is that, well, it turns out that we don't really need to solve the integrals and then understand the limit, but this function has been proven that it can be computed by summing the values of a certain rational function on the 2 critical points of the likelihood function, okay? So we can define this function here, okay? This is called the likelihood function. We compute it's 2 critical points, okay? We plug into another rational function that is not so relevant for us, and we get this amplitude, okay? What is interesting for us, though, is that the number of these critical points, so this likelihood function, is also measuring the Euler characteristic. So it's giving us information on the complex geometry of M05, okay? So as a complex surface, this has Euler characteristic, the Euler characteristic, so, yes, I wrote it here, sorry, Euler characteristic of the complex surface, okay, which is 2, okay? So what we have seen is that, well, somehow understanding, so for them, like computing this integral for us is interesting. We can see real geometry, the real geometry of the M05s comes into the game, the complex geometry of the M05s comes to the games. Also tropical geometry in this example maybe was not so evident. We will see it in a bit more complicated example. So it's really somehow opens up a lot of interesting questions also from the point of view of geometry and combinatorics, okay? And in particular, turns out that this positive region inside the compactification of M05 define a positive geometry which has this canonical form, okay? And I will tell you in a bit what this means being a positive geometry. So these few slides at the beginnings were just work as an introduction to the type of questions that arise when looking at this scattering amplitudes integrals from the point of view of an algebraic geometry, okay? So we can ask questions about real geometry, tropical geometry, complex geometry, and this boils down at the end to understand what a positive geometry is. So now I'm gonna do this for other example and give more definition and go a bit more through all the various steps for the Petzl surfaces in particular. Yes?
Sorry, I think I missed something. The number of critical points is Euler characteristic is basically Morse theory? Morse theory? Euler characteristic is number of critical points?
Yes, you can, yeah. Okay. So the example, the integral that I show you was just an example. I mean, in general, we can do it with n particles, okay? And then we will be interested in looking at M0n positive, okay? Another integral that has been introduced by Arkani, Ahmed, He, and Lam consider, similar, integrate similar function, but now over x3n, which is the moduli space of n points in general position in P2. Okay, so we move from P1 to P2, points in general position. And then the CGM amplitude instead, consider again similar sort of function, but now integrating over y36 plus, where this is for us is the moduli space of Mark cubic surfaces, of the Petzl surfaces of degree 3. Okay? So this is just to give you an idea that there are several interesting spaces that appear in this scattering amplitudes literature. Okay? So then let's...
X3n is what? The quotient of M0n by the symmetric group?
No, so I moved to the projective space, so to P2, to the plane. So, okay, yes. So actually this is coming now more precisely the definition. So, okay, so in general, we are looking at points in the plane, okay, and I will be focusing mainly on 6 and 7 points in the plane. So once again, by modeling out a projective basis and a torus action, I can represent them as a matrix of this form. Here I did for the 7 points case. You remove the last column, you get the 6 points case. So when I talk about x36 and x37, I look at points that are in linearly general position, so I don't want 3 points not on a line, okay? So once again, this means that now the Plücker coordinates, so the 3 by 3 minors of this matrix do not vanish, okay? So we can think of this as a quotient of the Grassmannian and so on. Now, inside of these two spaces, I can look at y36 and y37. So, and these are points in general position. So I also ask that 6 points are not on a conic. Okay? And this boils down to ask that some binomials, which we call them Plücker binomials, such as this one, so of degree 4, in the Plücker coordinates do not vanish. Okay? So also in this case, we can express the condition of not being on a conics in terms of polynomials in the Plücker coordinates, okay, of this matrix. Okay, so then x36 and y36 are very affine varieties, so they live in an algebraic torus. of dimension 4. And X37, Y37 are a very affine variety of dimension 6. Okay? At the same time, we also know that now if we pick 6 points in a general position, so 3 not on a line and 6 not on a conic, and we blow them up, we get a Del Pezzo surface. So in the case of n equal to 6, we get a Del Pezzo cubic surface, okay, so surface of degree 3. In the case of 7 points, we get a Del Pezzo surface of degree 2, and we all, this is very known for many, many years, that there are special, in general, special configuration of lines on such surfaces, right? On a cubic surfaces, we see 27 lines, and on a Del Pezzo surface of degree 2, we see 56 lines, okay? And the spaces are also very interesting, well, because they have nice symmetry, so there is a E6 action and a E7 action that acts on the lines configuration on the surface, okay? And, well, we know from work of Naruki in the 80s for Y36, and then this was conjectured by Sekiguchi and proven by Hakin, Kiel, Tevelev that, well, we can compactify these spaces, okay, and this compactification are smooth, their boundaries are normal crossing. So these are very nice spaces with so very interesting properties, okay? So now what I would like to do, I want to go through the complex, the real, and the tropical geometry of these spaces and try to put everything together and understand why they're, so what we can, how we can use them to build up to define a positive geometry on these spaces. Okay?
Sorry,
yes?
Why did you exclude the case n equal to 8?
The physics excludes the case n equal to 8. So the problem is that for the case n equals to 8, then you also need to include cubic conditions. So you don't want only the points not to be on a conic, but also not to be on a cubic curve that is pass through, with some conditions on passage through the points. And they don't care about this condition. So they consider also 8 points, but just the conic condition. So this is some sort of hybrid space. It's not the Del Pezzo of degree 1, because they don't impose, they don't ask another genericity condition. So we also consider it partially on our article, but it's not they're not the Del Pezzo. So that's, but indeed, also in this case, there are configuration of lines that are known and things like this. Yes, yes, but that's why we didn't, yeah. So for the physicists, they consider more this hybrid space. Thanks for the question. Indeed, it's a good point. More? Okay, so now let's start with the complex geometry. Okay, well, any the Pezzo surface of degree 3, so cubic surface in this case, has 6. I'm going up 6 points, okay, and I remove the 27 lines. Well, then this has Euler characteristic 19, okay, and this drops when we see Eckert points. Okay, so Eckert points means that 3 lines intersect in a common point. Okay, so when we see this, then the Euler characteristic will drop by the number of Eckert points that we see. Okay. We also understand the Euler characteristics of the moduli spaces. Okay, so this was computed before by Bergvall and Gunelas. Okay, and they use cohomology techniques. Instead, we look at a fibration, okay? So I can forget, if I forget the 7 points, I can go from Y37 to Y36. The problem is that in general, this is not a fibration, so the fiber can have different Euler characteristics, sorry. So this is what's called a stratified fibration. But if you understand the strata and you put it together with the combinatorially, there is also a way of understanding, of recovering the Euler characteristic of Y37, okay? So what we did is indeed is an analysis of the poset structure of this fibration and the Euler characteristic of the strata and the fibers. And somehow this is interesting because we can also see it in the comparison with X36. So Y36 lives inside X36. We're imposing one more condition, that we want the 6 points not be on a conic, okay? So if you want, like, the boundary is when indeed we have the 6 points on a conic, okay? And this is indeed M06, okay? So we see, so this is an example of sort of like strata analysis that we have done, right? So we know that the Euler characteristic of X36 is 26. The other, for us, Y36 was 32. And the difference is indeed the Euler characteristic of M06, okay? And something similar can be done also for Y37, okay, and X37. Now, the boundaries will be when we have 6 out of 7 points that are on a conic, and then there is a further degeneration when the 7 points are on a conic, and this really can be reinterpreted and re-seen nicely in terms of the Euler characteristic of these two spaces and the various strata. Okay. Now, if we move to the real geometry, so we're going to look at the real locus of these spaces. And what we computed is that Y36 has 432 regions. The closure of each is homeomorphic as a 4-dimensional polytope, which has this F vector here. Okay, so we have 45 vertices, 90 edges, 60 3-dimensional faces, and 60 2-dimensional faces, and 50 4-dimensional faces. 3-dimensional faces. Sorry, the jet lag. I feel like it's okay. And this polytope in particular is also like a simple polytope. Okay, and Y37 instead has a bit more than 60,000 regions, real region, and the closure of each is homeomorphic to a 6-dimensional homology ball with a certain F vector. So this is number of vertices and number of top-dimensional facets, okay? And I will come in a second to why we have here polytope and here homology ball. So the wild groups that act, as I said, on the spaces really permute these components. Okay, so they are all equivalent under VE6 and WE6 and WE7 action. And by abuse of notation, we call both this region, and in the case of E6, the polytope, as the pezotopes. Okay. So this result builds on several work. So Sekiguchi and Yoshida prove that that the actions of the Weyl groups on this region is transitive. Hakin-Kiel and Tevelev, they gives a combinatorics of the pezzotope, so they gives a description of how the combinatorics of the pezzotope should look like, using, so this is basically they look at these graphs and they describe, so yeah, let me just say, the combinatorics is encoded in these two graphs, and is really given in terms of root system and subroot system for describing vertices, edges, and so on. What we provide are, well, different, and I will get to that, realization of this curvy region, and in the E6 case of the polytope. Yes, so the difference in the two statements is that for the Y36, we were able to compute a convex realization of the polytope. So really compute vertices, and if you take their convex solve, you get a polytope that has this F vector and has the same combinatorial structure of the boundary of this region, okay? We were not able to do this for the Y37 case. So the computation became too heavy, and we were not able to terminate this, but we will get back to it, okay? So what we did, we define, also in our case of Y36, we gave equation in these 15 coordinates, okay, that for similarity of M05 we also called U coordinates, okay, and this they define a perfect binary geometry, and in particular they also give an embedding of Y36 in the algebraic torus of dimension 15, and the solution set, if we look at the solution set in R15 positive, this gives a realization of this curvy region, of this E6 isotope as a curvy region. Okay? So also in this case, so these are, they form a binary geometry. So a binary geometry is something that can be defined for simplicial or simple polytope, if you take the duality, is the same. So the idea is that you, from the combinatorial structure of your polytope, there is a recipe for building up equations that looks like this form. So in our case, there is the equation corresponding to a vertex plus products of other coordinates, and this somehow comes from the combinatorial structure of the polytope. Now we say that we have a binary geometry when this system of equations define a varieties that has the same dimension of your polytope, okay? So in our case, we expected the polytope to have dimension 4, or like this bounded region to have dimension 4, and so that's what's happening. So this, if you compute like the dimension of the varieties defined by this equation, indeed it has dimension 4. Okay, and moreover, you ask that when you put some variables to 0, the equations that are left describe the boundary strata of your region. Okay, and so this was happening in this case. So if we set the first 10 variable to 0, what we are left as are curvy asociahedra. So the regions are curvy asociahedra. If we set instead the last 5 variables to 0, then the stratas are curvy cubes. Okay, and this reflects the combinatorial structure of the polytope. Okay. So when this happens, we say that indeed this U equation defines a binary geometry. Perfect, because actually all the exponents with which the variables appear are equal to 1. Okay? So this binary geometry comes also from physics terminology, and they are still a bit mysterious in a sense, because they are also sort of rare. I mean, here we have 15 equations in C15, and they find like a variety of dimension 4. Okay, well, we will expect in general something of dimension smaller. Okay, so understanding actually from which simple polytope or simplicial polytopes has a binary geometry is something that we still don't understand. We only know a few examples, okay, of this. And in general, for example, understanding which one have a smooth binary geometry, so which binary geometry defines something smooth, this is also not clear. So there are still, somehow they are still a bit mysterious. Let's put it this way. And then using what we knew from the Euler characteristics, we could compute the E6 amplitude. Okay, so once again, evaluating the integral I show you in one of the first slides at the critical points. And what we get is this rational expression. And there is like a correspondence. So here we see 45 terms. This indeed corresponds to the vertices of our petzotope or our curvy region. So there is a nice, some sort of like very correspondence between. So we can still consider this realization actually of our petzotope. Questions about this? Now, yes?
I'm just wondering how you find these equations.
So you have to take, so one for each, so let's see. One for each, oops, sorry, what do I want to say? So one for each facet, okay? So you have one variable for each facets, U1, and then you have to take products of facets that are not adjacent to that one.
Okay, so these...
So there is a combinatorial way of defining this equation.
Okay, and I think you mentioned it in passing, but these binary geometries or these equations for binary geometries arise from polytopes?
Yes.
Okay.
Yes, so if you have a simplicial polytope or a simple polytope, depend like they're dual, so once we will work over the vertices, for the other one you will work over the facets. Okay, there is a way of writing down equation that looks like this.
Okay, so
okay.
you read off the equations
From the combinatorics of the polytope.
Right.
All right. And then the question is whether this equation actually defines something that has the same structure, boundary strata, of the original polytope. Okay. So yes, sorry, maybe I was not clear enough. So this is the trick. So you want so in our case, we wanted that this equation define a variety that has dimension 4. And when we set some of these variables to zeros, we look at some boundary strata, and this boundary strata should correspond combinatorially to one of the facets.
But maybe I'll ask this later, but if the answer is too long, but is there any reason to expect something like this to be true?
No, that's what I say. We don't know why. We don't know why. We don't know in which cases it works. So it works for M0n, okay? So this dihedral coordinates gives, in fact, a binary geometry for M0n. But there are only like few cases in which we know that this works, okay?
I see the strangeness now.
Yes, yes. And so that's still like up to further understanding, I think. So which you can also define this actually for simplicial complexes more generally, like with some nice property, okay? But again, like for which simplicial complexes works is still very much unclear. But when it happens, it's nice. You know, you get nice equation, and you really understand. They reflect very much the structure. And so, for example, in the case of Y37, okay, we also, we can cook up once again equations that looks like the previous one. But we were not able, for example, to compute the dimension of this variety because it becomes too big, and computer algebra software were not terminating. So in this case, we don't know that this defines a binary geometry. We expect to be the case. But we studied like. So yeah, we still are able to compute the E7 amplitude from some computer algebra computation involving some Steiner-Reisner radial and Alexander dual, but we still don't know. So we still notice this combinatorial isomorphism on this boundary structure, but we don't know if the full region has the right dimension. Okay. Now, more on 6 and 7 points in P2. So we could consider also a different way of representing 6 and 7 points in P2. Now, we know they always lie on a Cospedal cubic, so we can pick the simplest Cospedal cubic, and then we can represent the 6 or 7 points in this form. Okay, so this is after an automorphism of P2. Now, when we choose this representation, what's very nice is that when we ask the 3x3 minors, so if we look at the 3x3 minors and the conic condition, these factors in this linear form, okay? So di minus dj's, sum of 3 di's, or sum of 6 di's, okay? So these linear forms define the hyperplane arrangements of type E6 and E7. Okay, so in the first case, we have 36. In the other case, we have 63 hyperplanes. And this is the reflection arrangement of E6 and the type E6 and E7. And indeed, this hyperplane arrangement, they generate the Weyl group. Okay? And we can still consider the complements of this hyperplane arrangement as a parameterization of the moduli space of 6 and 7 points in general position. So whenever we pick a point outside of this complement, it will give us points that are in general position. So no 3 on a line, no 6 on a conic, and we can blow them up and so on. Okay. So now we can use this in the case of Y36, we can use the 36 linear forms to define a map first from P5. So we have 6 di to P35. And then there is a monomial map to P39. And this gives so we can define, I don't give you the precise definition here because maybe it's not so relevant, okay? But there is a rational map given by 40 polynomials of degree 9. And if we look at the closure of the image of this map, this is what's called the Yoshida variety, okay? And its open part is a way of embedding Y36 in P39, okay? And this was considered in work of Colombo, Van Game, and Loihenga, and again, Harkin-Kiel, Tevelev, okay? So a different way of realizing Y36, now inside a very big projective space of dimension 39. If we tropicalize this map, which is like a linear and monomial map, the tropicalization looks like a linear map between the Bergman fan of E6. We learned today what the Bergman fan is, in this case of this hyperplane arrangement, and the tropicalization of the Yoshida variety. Okay? So the polyhedral structure of the Bergman fan and the tropical variety and the map was studied first by Wren, Sam, and Strumfels. So in particular, these are very big that fan, okay, with a many top-dimensional cones, okay. And then, so first computing the Bergman fan of E6, and then applying this linear map, they were able to compute the tropical Yoshida variety, which is as dimension 4, and this is the F vector, okay? And Wren, Shaw, and Strumfels later on use this realization of Y36 and tropical Y36 to study, to look at types of tropical cubic surfaces, okay? And so this, they show that they come in 2 generic types. They are contractible, and they are characterized at infinity by 27 metric trees, which correspond to the 27 lines that usually lies on a cubic surfaces and also on a tropical cubic surfaces in this case, and they are now mapped at infinity, okay? So what we did, we took their data, and assuming that the generators of the ideal defining this tropical Yoshida, the Yoshida variety, are a positive tropical basis, we use it to compute the positive parts of the tropical variety. So now the positive tropical variety Y, okay? And what we notice is that this is, it turns out to be a fan with F vector 15, 16, 90, 45, okay? Which you should remember from some slides before, but written in a different order, okay? So it turns out that indeed, in this case, this is so it's combinatorially dual to the pezzotope, okay? So this is the tropical positive Yoshida variety is the normal fan of the pezzotope. So also via tropical geometry, we get a way of realizing this pezzotope and this real region that we are interested in with, okay? And we did similar computation for 7 points in P2, and the Del Pezzo surface is of degree 2. So there is a similar way of constructing, of realizing now Y37 as a variety in a big projective space using the hyperplanes in the arrangement E7 and so on, okay? And this was also, so there were also in this case computational data computed before that we used to understand their positive part. Still, we don't have, so we are still missing a realization of the pezzotope E7, okay? So we can remark again that this fan has the dual structure of the pezzotope, but we don't know if it's really the normal fan of the pezzotope, okay? Because we are missing the realization. Okay, and in fact, we wonder whether the fact that this is really the normal fan of a polytope can follow from general properties of positive parts of tropical variety, or maybe from properties of binary geometries using the previous approach. Okay, but once again, we don't know enough about this to conclude this. But yes, to conclude, let's get to what a positive geometry is. So without giving the precise definition, which is a bit of a mouthful, let's intuitively, informally, when we talk about a positive geometry, we are considering a semi-algebraic set, okay, which in our case, we should always think like positive points of an algebraic variety, equipped with we want a top degree rational form, which is allowed to have poles along the boundary of these regions, okay? And the residue along the boundary should reflect the structure of the region, okay? So in particular, for M05, this was the canonical form that I gave you. This is in terms of the U coordinates. And we see, for example, that if we look at the residue along U2 equal to 0, we see the canonical form of a segment, okay? So we expect a pentagon, right? And that's what we see, okay? And so this notion of positive geometry was defined by Arkani Hamed by Elam in 2017. And they prove, for example, that polytopes, positive parts of tropical varieties, positive parts of toric varieties, the non-negative Grassmannian are all examples of positive geometry. There's been like some recent work by, well, this is a paper with a lot of authors in which they study polypoles, so generalization of polygons, but where the boundary can be curvy, okay, and they prove that they are positive geometry. Some semi-algebraic subset of the Grassmannians of lines in P3 are positive geometry. There's been defined some generalization of the non-negative Grassmannian, showing that it's positive geometry. And in general, the technique that I use in all these papers goes by looking at adjoint hypersurfaces. But recently, there's been, at the beginning of the year, there has been a preprint by Francis Brown and Clément Dupont, in which they connect, so the existence of positive geometry, so they provide a recipe to define a canonical form, looking at the mixed Hodge structures of the variety that you are looking at, okay? So in our case, we were able to prove that each of the 432 real regions of Y36 define a positive geometry. Okay, they are all equivalent under this wild group action, so you actually have to prove it just for one, okay? And in particular, if we pick the region which we call the pexotope, so the positive region, this is how the canonical form look like, okay? And somehow, like the technique that we used was to deduce this canonical form from the known canonical form of X36. Okay, so one of our co-authors, Nick Early, comes from the physics approach to the story. So he knew how. So he had more of a sense of how this canonical form should look like. He knew how they would look like on X36, and he was able to, guess it in some sense, okay, or for Y36, okay. And indeed, then we could prove that this recursive structure of the poles is preserved. But we couldn't do this for Y37. Okay, because then the computation were getting too complicated, so his techniques were not working. Now, from the work of Francis Brown and Clément Dupont, we know that this region in Y37, so we know that Y37 admits a canonical form, okay, because they satisfy the hypothesis that they consider in their work, and they give a recipe for giving like a canonical form, describing a canonical form. The problem is that it's not very, so it's still very theoretical. It's not maybe so computational in this type of space, when the space becomes this big, okay? So we know that there is a positive geometry structure on it, but we still cannot produce the canonical form. And with Claudia Yoon and two other co-authors, we are trying to make a bit their approach a bit more explicit, specifically in our case, to get really the canonical form, because that's what's interesting for the physics. So really understanding, so out of knowing that the space admit such a forms and allows so they control the poles along the boundary, it's what's interesting and what's relevant for them, okay? So that's ideally where we want to get, to use all the machinery, we understand the complex structure, we understand the real structure, we know the tropical geometry allows us to understand the real structure even further, and the idea would be to then put everything up to be able to define, to write down such a form. We manage in Y36, but not for Y37. And that's all I wanted to say. This is the E6 pezzotope, of the Schlegel diagram of this E6 pezzotope.